Suresh. I'm a software engineer at NCAR. We mainly work on porting and optimizing climate modeling and weather modeling codes onto GPUs. For this presentation, I'm presenting one of the model that we have ported onto GPUs. This is going to be the outline of my talk. I'll give a brief introduction about our team and the introduction about the model, the system and the software specs that we are using, and the approach that we took, and the challenges, some of the challenges that we faced, and the performance numbers that we have achieved in both dynamical core as well as physics. So this is our team of developers. This is a multi-institutional project. We have myself, Sina Miller, and Michael from NCAR. We have a small team from NVIDIA, which is supporting us with the GPU work, and but our main backbone is the research graduate student and undergraduate student from University of Wyoming, and we have had support from IBM currently, and we have had support from KISTI as well. So yesterday, Dr. Raguraj gave a brief introduction about MPAS. So I'm just going to build on top of it. So MPAS has an unstructured mesh. One of the main advantage of MPAS grid is you can actually run finer resolution at certain regional areas and the remaining globe at a much coarser resolution. MPAS has a honeycomb structure wrapped around the globe, and it provides some good scalability on CPUs. Going to the vertical structure, we have advantages like terrain following, which also improves the numerical accuracy. So when we dive into the code, this is the default time integration step. So first there is a call to physics code to obtain all the parameters, and then and then the code goes into the dynamical core, which solves the differential equation to move in time step, and then there is a call to microphysics. We have had numerous number of presentation about the dynamical core, so I'm not going to get into that. So one thing I wanted to highlight is there are hundreds of calls of Halo Exchange in the time step. So we started this project back in 2016, and we have optimized dynamical core, the functions in the dynamical core a lot. But one of the main problem we faced was the Halo Exchange calls. How did we start? We looked at the profiling results. We saw the two main functions are the physics and the die-core. We saw the lines of code. Die-core was only 10,000 lines of code. We started porting that, and then we went inside the physics. So for our performance results, we are using for CPUs, we are using NCAR Shan supercomputer, which has 2-socket Broadwell nodes. We are using Intel 19 compiler. And for GPU results, we are using Summit supercomputer and also the IBM WSC supercomputer. So in Summit and as well as WSC, we have a 2-socket Power 9 CPU with 6 GPUs per node. So going to the software specs, in the dynamical core, currently we are using MPAS 6.x, the GPU code, but the current latest version of release code is MPAS 7. So we are in the process of moving to MPAS 7 as well. For GPU executions, we are using PGI 19.4 compiler. For CPU execution, we are using Intel 19 compiler. For just the dynamical core execution, we have a test case called baroclinic instability test case, where we can just run the dynamics without invoking the physics. So for our runs, we are using all the way from 120-kilometer resolution up to currently we can run the code with 5-kilometer resolution, which has about 23 million points in it. And we are sticking to like 56 levels, vertical levels at present, but we plan to increase that as well. And all of this runs are in single precision, and the performance I'm going to show is for one time step. Going to the physics software spec, we have something called meso scale reference, in which we have all of these physics schemes. The ones in the blue are executing on GPUs. The ones in black are executing on CPUs. So currently the optimization and integration is in progress, but we are very close to porting full MPAS on GPU. So I'm going to talk about it in the next slides. So one of the things when we started was, one of the things that was bothering us was whenever you port applications or code onto GPU, most of the CPU resources, when GPU kernels are being launched, most of the CPU resources will be idle. But what we wanted to do was we wanted to utilize the whole heterogeneous node. We didn't want to waste any resources on both CPU as well as GPU. So this diagram is how we are mapping the processes on an IBM node, for example. So we have a few reserved MPI ranks, which launches GPU kernels onto the GPUs, but the remaining number of cores or the number of process on the CPU will be executing something asynchronously. I'm gonna talk about how we are dividing that between the CPU and GPU in the further slide. And we want to dedicate some cores for doing the I/O as well. So as I mentioned, one of the main problem that we faced after porting few functions from the die core is the MPI Halo Exchange. Originally, the Halo Exchange was written using linked list, and the OpenACC just loved it. So we couldn't get any performance, or we couldn't even get to execute on GPUs. Actually, MCube rewrote this Halo Exchanges using just arrays, but some parts were still kept on CPU. Again, we requested them to rewrite in such a way that all this bookkeeping will be moved on to the GPU, as well as the bottleneck like send and receive buffer allocation. Once they rewrote it, there were no CPU overheads, but we still were seeing some less performance than what we expected. So what we did was we looked at the profiling using NVProf. So we saw two sets of kernels. We saw two sets of kernels here. The first set is packing the buffer for sending, and the next set of 9 kernels is unpacking the buffer and receiving it. When we zoomed into the sending part, for example, so this execution is on a 4 GPU, and MPAS uses a triple layer Halo Exchange. So we have 3 neighbors with 3 layers. So we have 9 kernels in total. So the profiler indicated to us that for each send, we are packing the buffer individually and sending it individually. So that was a lot of overhead. So what we did next was we nested those loops closely. We actually pushed the loop inside so that we will be launching less number of kernels, and thus minimizing the overhead of kernel launch as well as kernel launch as well as the data transfer. So this dropped the MPI overhead by 50%. That is from 0.11 to 0.06, I think, approximately. So we after optimizing this Halo Exchange, we further looked into the dynamical core to see what all we missed in the first go. So we had some module level variables which were dynamically allocated and then unnecessarily copied in every time step. So this was undesirable because we don't want data copy in every time step. So what we did was like we just initialized them on GPU so that it will be resident as a GPU variable. Similar thing happened in one other important routine as well. So the intent was one of the major function. So here also we saved some time. Originally, MPAS reconstruct was kept on CPUs, but then we ported that to GPU as well so that we get a good flow of execution on GPUs. So one of the things that we found out was if you have a mixed Fortran 77 and Fortran 90 array syntax, this caused the compiler to think that there is no parallelism and it would just serialize the whole execution. So we had to rewrite everything in Fortran 90. And lastly, like we had the code was printing out the summary by default for every single time step. This is undesirable because we had to come back to the host. We had to copy the data again to the host to check the answers. So we just commented it out. But whenever we want to debug, if we feel something is not right, then we would enable this function and check the values. So after all this, we started executing MPAS at a very high resolution. So one of the problems that we faced was the initialization time for MPAS was way too high when we were using NetCDF4. I don't know the reason behind it, or but when we switched to CDF5 file format, we got a good scalable performance in the initialization time as well. So after doing all of this optimization, we got some good scaling results, both strong scaling as well as weak scaling. So here is my strong scaling setup. So the test case that we are using is the moist dynamics. Till now we have been showing the dry dynamics, but this first time we are moving over to moist dynamics from now on. So for GPU execution, again we are using 19.4 compiler, PGI compiler, and for CPU we are using Intel 19 compiler. For the test cases, we have taken 5 kilometer, 10 kilometer, and 5 kilometer with 56 vertical levels. So this is the strong scaling graph at 10 kilometer. This is a comparison between Summit and Shan. So here you can see the code on both CPU as well as GPU scales very well. But the first point, I think that is 72 nodes versus 72 GPUs. You can see a good speed up between the CPU and GPU. But once you hit after I think 170, 180, you're starting to see trailing off because the GPU does not have enough parallelism to exploit there. So this is the strong scaling graph of moist dynamics at a 5 kilometer resolution, which has 23 million data points in it. Here I don't have any comparison between CPU and GPU. I just have the data for GPU here. Here we are using up to 1500 GPUs on Summit. This was achieved very recently, so one of the reasons we didn't have enough time to do it on CPU, so we don't have the comparison yet. Going to the weak scaling. Weak scaling is nothing but we are keeping the amount of work per node or per GPU constant, and we are increasing the resolution. So here also we are using a very similar setup, PGI compiler, Intel 19 compiler, but the resolution, it goes from all the way up from 120 kilometer resolution to 5 kilometer resolution. So looking at the weak scaling graph, like typically a weak scaling graph should be flat. Here for the data point from 1 to 3, there is a bump. That's because for the first point, we don't have any halo exchange communication. When you go to the second point, you have 3 neighbors, that is 1 to 4 GPUs. So from 2 to 3, third point, we have from 3 neighbors all the way up to 7 neighbors. That's why there is a bump in both 40K points per GPU and 80K points per GPU. And after that, there is no communication overhead, though, so it stays flat, almost flat. So going into physics, so we have completed most of the physics porting onto the GPUs. But the reason it took a lot of time for us was we are building a methodology, because as I told, physics is hundreds and thousands of lines of code. We wanted some of them to run on CPU and some of them to run on GPU. In that case, the validation became so hard. The validation and the integration, we couldn't actually verify any of the answers properly. So what we thought of was to build a methodology. I'm going to explain about this methodology in the next slide. But the blue colored points indicate all of these tasks have been done. We are only remaining with one physics module to port onto the GPUs or optimize onto the GPUs. So the methodology looks like this. So we have some markers in the code this helps us to actually search where we are debugging. When we obtain some wrong results, so we actually start running one by one on CPUs. This can be achieved by including a preprocessor directive like -d GPU debug WSM6. So in this way, we can actually flip any of the physics routine to run either on CPU as well as GPU. With this methodology, we are just updating the host, because if we want to run on CPU, we want to copy all those results back to the CPU. And then we run the code, and then again at the end, we'll have one more update device directive, which updates all the data onto the GPU again, so that the GPU flow will continue. And we included all these debug statements for the OpenACC directives as well, so that we can just flip whenever we want. We can just flip back to CPU execution or GPU execution. So we repeated all these modules. We repeated this methodology for all the modules. So we can remove, but we plan to keep this. Or it depends. If you wanna debug at a later stage, that would be helpful. So this methodology includes the required data transfer when we are running few of the modules on CPU, like no LSM and radiation code. So this is the full projected MPAS performance that we hope to achieve. So we planned 0.18 for dry dynamics, for the dynamics portion, which includes dry dynamics, moist, and halo exchanges. So we plan for 0.22 seconds per time step, but we are at a phase where we achieved 0.18. We are in the process of optimizing this physics modules. So we haven't fully validated it for broader test cases, so we are just not showing the results today. So in going to the future back, the things that are remaining are we want to optimize these remaining physics schemes, and we want to verify and integrate these physics schemes that are remaining, and we want to integrate this lag radiation into our GPU code, so that lag radiation will execute asynchronously on CPU, and at the same time GPU will be executing the dynamics and the remaining physics portion. Thank you. Questions?